Hello, class. I seem to be recording. Excuse me. Got some water and I have some tea. Nice warm tea. So I thought that I would continue on looking at our three nodes that we had in that relatively complicated looking circuit in the last lecture, and how we simplified the circuit into the three nodes that we have: A, B, and C, right? And then all of the other resistors that were attached to that very complicated looking circuit that we had, we just worked out what was in parallel, what was in, we expanded the node out where we had a lot of connections. So I think everybody saw how I did that. And we're really looking at something here that still is a series parallel combination. So I'm going to put that up here: series parallel combination. So that's what we're looking at, and we've simplified it down to this point. Now we're going to use the Kirchhoff's current and voltage laws that we've seen before, and the simplification of the various series and parallel capacitors to further simplify this circuit, so that we can figure out at any of the individual nodes that we have here what the voltages are. And so that's what we want to look at. Let's just write down what we want. We want, in fact, I'll put it over here. We want V sub A, V sub B, V sub C, those three voltages. We then are going to want, and I'll use some different colored pens here, we're going to want the current that's coming out of the, I'll use a blue pen, that's coming out of the power supply. And then we want to see how that current breaks off as it goes through all of these various different resistors throughout the entire thing. And we can do that by looking at, by figuring out voltages and voltages at different points, and then looking at the resistors that are going through those different voltages. We look at a voltage differential plus the value of the resistor, and we can figure out what the voltage drops are and everything else. Very straightforward process. So that's the first current, and then the currents are going to change, of course, as they go around. That first current, of course, is also the current that's coming back in to the power supply, isn't it? So let's see if we can simplify the circuit a little bit more so that we can see what the resistance is down here. And to do that, first, we have to come up with each of those 8 resistors. So let's just think of common resistor values. Just a second, I'm just going to flip back. Where did I see those? No, I don't, oh, where did I, no, I thought I, oh well, we'll use common resistor values anyway. All right, so let's go from R1 to R8. And I like to, just choose these randomly because, doing the problem, it doesn't matter. I don't like to just, get canned problems and then just do it. So let's just pick some resistors and randomly put them anywhere in this thing. Let's say that R5 is going to be a 330 ohm resistor. R2, I'll make that a 390 ohm resistor. Okay. And then that'll be a 270 ohm resistor. I'll make R8 a 100 ohm resistor. And then R6, oh, I don't know, a 120 ohm resistor. R3, we'll have a 220 ohm resistor. Trying to keep them all sort of, within the same ballpark. I don't want to throw a 1 mega ohm resistor in there and just throw the entire thing off. So I've got a 180 ohm resistor. And then for the last one, let's make it a rather large resistor. That would be 470 ohm resistor. There you go. So I've just picked 8 different resistors, and we originally had them in that configuration that we had in the last lecture. I've just picked some resistors here. We now have them in this, and we can still simplify this further, can't we? Because I think you can see some things that are in parallel and some things that are in a series, right? So if we look down here, we see that these 3 and 2 are in parallel. So the first thing that I want to do is to redraw the circuit, and I'm going to put the 100 volt power supply in there too. But let's redraw the circuit, and let's get rid of a couple things here. Now this, if we do put those two together, we'll come up with a common one. Maybe I don't want to get ahead of myself. So let's just leave it like it is for right now, and we'll do it step by step. So that is 8 and 7, right? 1, 8, 7, just like it was. And we've still got 6, and we've got 5. We've got 4. I'm going to leave that there for a second. And then what we want to do is we really want to combine those two, right, in the 2 and 3 in parallel. So that's really a 2, 3 in parallel. And what is the value of that in parallel, right? So 2 and 3, 390 ohm and 180 ohm in parallel. That would be, so I'm going to just write that down because, I've sort of, wait, yeah, 2 and 3 in parallel. So if we do 2 and 3 in parallel, I'm going to write it out like I would usually write, 390 ohm in parallel with a 220 ohm resistor. Now, what does that do? We have 1 over 390, right, plus 1 over 220. I should put my ohm symbol there, but this, this is not the finest point Sharpie in the world. 1 over 220 is going to give me the 1 over the equivalent of those two, right? Or really the 2, 3 in parallel thing. So what that tells us is that the equivalent resistance, and of course these two in parallel, the first thing that you want to say is, all right, that's 320, that's 390, that's 220. So it's got to be less than 220 ohms, right? It's got to be less than 220 ohms. So if your calculator tells you that REQ is not less than 220 ohms, you know you've made a mistake. So that's sort of the acid test, and just, you may have hit the wrong button or something like that, but let's just do it. So we've got 390, 1 over plus 220, 1 over equals, and then 1 over that gives me 140.66. 140.66. And I want you guys to be doing this with your calculator at the same time that I'm doing it on here. So you can see what I'm doing, actually do it. The whole working out on your calculator, all of that will be stuffed into your permanent experience memory, and it'll be so much better. It's like Abraham Lincoln used to read out loud all the time, which made his law partner very nervous. And so I said, Abraham, why are you reading out loud all the time? And Abraham Lincoln said, well, that way I get it through my 3 senses. I speak it, I hear it, and I read it. I guess reading was a sense back then. That's sort of what you're doing. The more experience that you can have with solving problems, seeing how they're solved, putting these things together, and of course we've got that now. But hey, look at this. We've now got that, the 140.66, in series with R4, don't we? It's in series with that. So now we can redraw this again, because we'll have this in series with that, and I could draw it as, God, I hate to keep drawing these, but I will. And my pen is getting less too. So now we've still got that first resistor, still got the next two resistors, still have the resistor in between those. But now what I have is I have this resistor. I'm sorry, it's taken me a few seconds. And then this resistor here is going to be a combo, isn't it? It's going to be a resistor that is in series between this and this. So this resistor right here now is going to be 470 plus 140.66, or 610.66. I hope I did that right. Yeah, I'm pretty sure I did. So 610.66, and then the one that's right next to it, this one right here, which is number 5 right here, is now in parallel with that. So now what we've got, if we're going to keep doing this, so let me just put 7, 5. That's 2, 3. This was 4. This is 6. We've now gotten rid of 4. 4 is gone, and we've got this 610 in parallel with number 5. That's 5, still 7, still 8, still 1. I'm going to redraw that in just a second. Now, so we've got that 610.66 in parallel with 5, which is 330. So let's do that. So 1 over 330 ohms plus 1 over 610.66 ohms, right? And then I'm going to take that to the reciprocal, because we know that the equivalent resistance would be 1 over. So this just gives me the answer. So I've got 330 taken to the reciprocal, 330 taken to the reciprocal plus 610.66 taken to the reciprocal equals, and then take that answer to the reciprocal, and I get 214.2. 214.2 ohms. And how do we know that is that less than 330? Is it less than 610? Yes, both. So it fits into the acid test that we have. I forgot to put my timer on. And how would I know? I'm going to have to change. Let's say I've worked 10 minutes. I don't know, something like that. All right, so my timer is on now. Hopefully it's 10 minutes I've been going. I don't know. My throat sounds like, it feels like it's been going longer. All right. So now we can redraw this again, because we know that 5 and the combination that we have here is going to be 214.2. So let's redraw our circuit, actually a little bit better this time, because it can be a little smaller, can't it? We still have the resistor here, number 6, but instead now we have number 6 in series with this resistor that was 214, the equivalent resistance, 0.2 ohms. So this one down here, which is 6, is 120 ohms. So we'd add those two up, and of course this is still number 7, this is still number 8, and this is still number 1. Let me connect the bottom here as I'm running out of ink in this Sharpie. I think I've got other Sharpies right here, so we'll try those. All right. Now, I think everybody can see the next thing that I'm going to do is take the 214 and the 120 and add those together. And those will replace the one that I've got here, which will now be, if you can see this, if I add these two together, oh, that doesn't work at all. If I add those two together, that's going to give me 334.2 ohms. Now that 334.2 ohms is in parallel with 7, isn't it? It's in parallel with 7. Hey, you know what? It's in parallel with 7, it's in parallel with 8. So let's redraw that again. So now we've got our 100, we've still got number 1, but now we've got 3 that are in parallel. Right? Does everybody see that? And this one here is 334.2 ohms. And then the two that are next to it, number 7 and number 8, are 270 and 100 respectively. I'll write the 100 in, and I'll try to write the 270 in. So that's what we've got now. Now we've got 3 in parallel, and I see that the smallest one is 100. So I know that when I do these 3 in parallel, it's going to be less than 100, isn't it? So let's just see what that is. So 1 over 100 ohms plus 1 over 270 ohms plus 1 over 334.2 ohms, and all taken to the minus 1, right? Because I'm reciprocating it so that I can get R equivalent. And I should call these like R equivalent 1, 2, 3, all right? So when we put that in, and of course that's all going to be in series with number 1, which is 180 ohms, right? So 100 reciprocated plus 270 reciprocated plus 334.2 reciprocated equals, and then that answer reciprocated gives us 59.9. 59.9 ohms, and that's less than 100 ohms, isn't it? I think everybody sees that. So we still have to add that on to the 180. So our total, what the power supply is seeing of that circuit, is going to be 180 ohms plus 59.9 ohms. And you know, I wish it was 60, but it was really like 59.89. So I'm going to keep the 59.9 ohms. We're assuming the 180 is, you know, so our total equals 239.9 ohms, and I'm going to say that that's approximately equal to 240 ohms, and we can use that in the solution now of our problem, because what we're trying to find is V sub A, V sub B, V sub C, right? And we know now what that our total is, so we can now figure out what I is, right? This I right here, which I did in blue, the I that is coming out and then going back into the power supply. We can easily figure out what that is because we've got Ohm's law. Let's write Ohm's law up here. V equals IR, right? And my power law, P equals IV. And then we also figured out that that could also be I squared R, or V squared over R, right? So we've got all those various different equations that we have for all of the resistors to figure out what all the resistances are and everything else. But right now, we just want to find out what I is. And really, why am I trying to find that out? Because I want to find out what node A voltage is, don't I? And can't I find that out by finding out what the voltage drop is across that first resistor? That's right. If I find out what that voltage drop is across that first resistor, then I can just subtract it from 100 volts, and that tells me for the top of all of those resistors that are up there, what their voltage is going to be on that side of the resistance. And very quickly, that will help me decide what the voltage is at B, and then that will help me decide what the voltage is at C. And as I figure all of those out, I can then easily calculate what the currents are between all of those, and then we can figure out what all the power is that's going through each of those various different resistors, because it's the voltage difference times the current, right? The voltage drop across the resistor times the current through the resistor. That's what power is. So anyway, I'm getting ahead of myself. Let's just look at I. So I is just going to be V over R total, right? And V is 100 volts. And R total, well, we figured that out. We're going to use 240 ohms, which is pretty darn close to 239.9. So 100 volts divided by 240 ohms, wait, don't tell me, is 416.67 milliamps. Notice how I put down milliamps, because I like to work in, tens and hundreds and stuff like that. I could also say, though, that would be 0.41667 amps, couldn't I? And so we always want to, look at that. But that immediately tells us what the voltage drop is across R1. Because the voltage drop across R1 is going to be equal to the current flowing through R1, 0.41667. And like I say, always use the combination of primary units. You wouldn't want to use 416.67 milliamps, would you? Always go back to using the combination of primary units. All right. So that's the current. And then the resistance is 180 ohms. So this is telling us what the voltage drop is, remember. It's not telling us what the voltage is, it's telling us what the voltage drop is. So times 180 gives me 75. Wait, what? 75 volts? Oh, wait, yeah, okay. 75 volts is the voltage drop between this and this. And so what you can see is a lot of the current, I'm thinking, is going to be flowing down through here. So this spot right there, the voltage drop is 75 volts. So we could say that the voltage at A is going to be 100 volts minus 75 volts, or 25 volts. And so there's this whole bar up here that we've now put together. All that node is actually at 25 volts voltage, right? Does everyone see that? Okay, well, that's great. Hey, you know what? Look on the bottom. Look on the bottom here. We know that all of these are connected together, don't we? So we know that this current actually starts right here. All of these are coming all together. There's current that's coming down through here. Let me grab my other pen. There's current that is coming down through here. There's current coming down through here, right? all of those are coming around, and that's where a lot of the current, I think, is going to be flowing. Is going to be flowing down through these two resistors is what we're going to find. But we've still got you know, this at 25 volts, and we've got to find out what yeah, because all of these, if you think about it, the voltage that I've got down here, because it's grounded, right, is all 0. So I'm still going from 25 volts down to 0 through these resistors. The only thing that's stopping the current from flowing directly to 0 is because I've got two resistors here. Yeah, those, I could have made those larger. That probably would have diminished the other thing. But I wanted to just pick them out, you know, just like you would find them when you're doing a printed circuit board. You work with what you got. And that's why I tried to, you know, pick them at random. Okay, now, how would I find out what the voltage at B is going to be? Sort of running out of a little paper here, but here, let's do a couple first. Let's, you know, we've got to find a lot of current as well. So let me write down the currents that we've got to find. So we've got to find I. That's one current. We have to find the current through resistor 8. We have to find the current through resistor 7. Have to find the current through 5, 3, 2. We know what it is through 1. And yeah, actually the current through 4 and 6 would be totally different as well. So we've got all those currents to find, and we have the voltage at B and the voltage at C still yet to find, but we know what the voltage at A is, and we'll be able to figure out what all of these currents are as soon as we start to figure out what the voltage at B and the voltage at C is. Let me just check my time here. Oh yeah, no, I've got some time. Yeah, that's okay. So what we want to do is, if we look down here at the bottom, we know that I've got 0 volts right there, right? We don't know what the current flowing through 6 is, but if we did know what the current flowing through 6 is right now, and we'll look at that in just a second, because we can figure out what. Anyway, well, let's do that. Okay, let's just figure out what the current is that's flowing through number 6. How would I do that? Let's find out that what the current is that's flowing through number 8. So the current flowing through resistor 8. Well, what's the voltage difference across resistor 8? That would be 25 volts. Let's write that in here, 25 volts, because we're going to be using that throughout the solution of the rest of the problem. We know that's 25 volts, and we know this is 0 volts. So the voltage difference across there is going to be 25 volts, isn't it? And then what's the resistance of number 8? It's 100. 100 ohms. So if I was looking, 25 divided by 100, I think everybody knows, is 1/4. So that would be 0.25 amps. So IR sub 8, let's put a little box around that. We're starting, well, we've got voltage at A too. Then we've got IR, I don't want to get a, okay. How about the other one, the current that's flowing through R7? Couldn't we do the same thing with that? Isn't that also 25 volts? Except instead, number 7 is 270 ohms, isn't it? 270 ohms. So 25 divided by 270 ohms is 0.0925, or 92.6. I'll write it out, 92.6 milliamps, right? Wait a second. No, I've got that. Where's my correct tape? Sorry. Yep, that's why you do it in your head first. Yep, I should have mentioned it. Oh, wait a second. Oh no, that is right. 90. Because this, of course, I wrote this out 250 milliamps. I'm sorry about that. And this is 92.6. I did do that right. Oh boy, it's getting late in the day. All right, so let's look at what we've got now. Now we've got I r sub 7 done, I r sub 8, I r sub 1. That's really, because that's I that's flowing in there. It's flowing in through I r sub 1. And so we know what these are now. And we know what the total current is that's flowing out of the power supply. So can't we use Kirchhoff's current, right? Kirchhoff's current law to figure out what the, I'll use another color pen, what the current is that's flowing into that node from the rest of the circuit, right? Because this is the node right here. Here's the node. Let's just draw the node and the various different things that are actually going into it. There's the node right there. We know that coming out of that node, I have I, right? And we know that I is 416.67 milliamps. What's going into the node? Well, this is going into the node. Both of those, the current from 7 and the current from 8. So I'm going to put both of those. So I7 and I8 are both going into that node. I is coming out, but I7 and I8 are both going into this node. The only other thing going into this node is what's coming out of the rest of the circuit. I call it I6, right? Because it's flowing through resistor 6. So if I want to find out what I6 is, I just take I subtract those two off, and what's left over is going to be I sub 6. That's right. That's what's going to be I sub 6. And so I'm going to put it right down here. I'm actually going to use this last one. I6 is going to be I minus I8, which is 250, and I7, which is 92.6. So 0.416667 minus 0.250 minus 0.0926 gives me I hope I've got, yeah, 0.0741 amps, or 74.1 milliamps. Right, so there we've got another one. I sub 6 is now taken care of as well. V sub A is taken care of. We don't have V sub B, we don't have V sub C, but we're almost at V sub C right now, right? Because we know the current going through there, we know this voltage is 0, so we know, I'm going to put it right here, V sub C equals 0 plus the current flowing through, number 6, which we know is 0.0741 amps, times the resistance of number 6, which is 120 ohms. And that tells us, let me just put that in here, times 120. And that tells us it's 8.88. That's a point there, 8.88, that looks like an X. It's supposed to be a V volts. So we can put that one down here too. I'll just cut myself out a little piece here, and I'll say V sub C equals 8.88 volts. All right, we're going to leave it there because we now know V sub C. We know a lot of the various different currents that are flowing through all of our various different resistors. And in the next lecture, what I want to do is I'm going to set up a little table so that we can see what we've already done and what the circuit is like, and see what the voltages are, and then we can finish the voltages off and then look at power consumption, right? Look at power consumption of that circuit. So we've taken a very complicated looking circuit. We've used our simplification methods to get that down to something that's really parallel and series. In some circuits, you cannot do that, by the way. In some circuits, it's not going to be this easy to do. And of course, that's why we're going to look at the analysis methods later on in the course, both nodal analysis and mesh analysis. And that, of course, uses matrices and stuff. And so we'll talk about matrices and things like that too. But for right now, we're just trying to get down the basics of parallel and series resistances in the DC course. And we've gone quite a ways today in looking at these. We've still got to finish what it is that we're trying to accomplish. We still need, oops, I forgot to mark off V sub C, our last thing that we did there. What else have we got? Yeah, we don't have 5, 4, 3, or 2. But 5 isn't very far away, is it? Because we now know what the voltage at C is. We know 25 minus 8.88 is the voltage drop across number 5. So that should be very easy to figure out what the current through it is, right? Ohm's law, V equals IR. Okay, I'll see you in the next lecture. I think this is lecture number 9.